the day as part of our virtual reunion events this weekend. You know, we're certainly excited that we're able to do this, even though we aren't able to be on campus together. I'm happy that we have Aileen here today. And she's been part of the SLU community for quite some time. And when she's not busy with her work and research interests in radio astronomy, you can hear her on our local NCPR station giving a report of what to expect in the summer skies, or leading commencement with her awesome summer cat.
I missed that.
Yeah, I know. We all missed that this year. So, you know, a few notes before I kick it off to Aileen. She is welcoming questions at any time during her presentation. So you are able to use the chat function, or if you click on the participants, you're able to raise your blue hand. So we'll be monitoring that on our side. And so feel free to kind of ask a question at any point when Aileen is talking, or at the end. We'll definitely have some time for Q&A there. Another thing of note, you're welcome to turn your video screen on if you would like, but if you would just like to keep that off, that is okay as well. With that, welcome Aileen to our talk, Einstein, Eclipses, and Multimessenger Astronomy.
Okay, let me start my I gotta share the screen before I can do that. Where's my escape? Okay, share screen. There it is. Share. And now, here's this. Okay, so this is about the newest, greatest discovery in astronomy. It's probably the greatest discovery in astronomy in my lifetime. And it confirmed again Einstein's view of the universe. So in Newton's universe, space and time are independent and static. Nothing alters the dimensions of space. Nothing alters the flow of time. Matter and energy are completely distinct and separate. A rock, you can have a rock, it's matter. You can weigh it, you can melt it, you can vaporize it, you can throw it, well, melt it or vaporize it, but it's still stuff. And and then it can also have energy. You can throw it, you can drop it. It can gain energy, it can lose energy, you can put it on a shelf. It has kinetic, potential energy, but they're completely separate. So in Einstein's universe, space and time are not independent. They're what's called spacetime. Both are altered by motion, and both are altered by gravity. And so I had a question by email that if a flame sees another flame displaced in time, will it be the same color? Yes. If it's displaced by motion, then it won't. If a flame is coming at you, it'll appear bluer. If it's going away, it'll appear redder. It's motion that changes it. So, and then Einstein said, matter and energy are the same stuff. Matter can become energy. Stars shine by doing this. Every second that we're on this screencast, and every second you are asleep or awake or bored, the sun is turning 45 Enterprise type battleship aircraft carrier masses worth of hydrogen into complete energy. The hydrogen is disappearing into energy, and that's what comes to us as sunlight. Energy can also become matter. Now that's harder. That happened in the Big Bang. That's where all the, the initial hydrogen and helium came from. So the stuff of Einstein's universe, there are these symmetries. There's matter and energy. So basically there's four things in the universe: matter, energy, space, and time. And so matter and energy go together as different forms of the same stuff. They're related by E equals mc squared. And then space and time are related they're both kind of constructs of this universe. And the way I think of space and time is they provide the scaffolding in which matter and energy do their thing as stars and humans and puppies and flowers. And so we can show our universe. You know, we're used to having a three-dimensional grid up and down, side to side, back and forth. Well, now let's turn that, because we're all getting dragged into the future 1 second per second, whether we want to go or not. And as you get older, you know, you get dragged into the future 1 minute per second. And so let's turn it. And so we bring that, we have two axes in space and one in time. So there are the space axes measured in meters. Here's the time axis measured in seconds. Well, if we want to draw accurately, we need to know how many meters there are in a second. There's 3 times 10 to the 8th, which is 300 million, or 186,000 miles per second. A second is really big in the universe compared to a meter, or maybe we're really tiny compared to a second. So what Einstein said is that all this stuff in the first 10 to the minus 43 seconds of the universe is that space, time, matter, and energy was all squashed together. Now, if you squash the structure together with the stuff inside, it's, how do you describe it? All of our physics equations get written with T for time and X for space, or R or Y or Z. And if those things can't be separated from velocity, from mass, how do we write any physics equations? We don't yet know. This is what really smart people like Stephen Hawking have been working on. It's all the same stuff. And, you know, when you have a problem, the first thing you need to do is name it. So we've named it quantum foam. It's the same stuff we think that's in the middles of black holes. And we don't know the physics. We can't write down the equations because we lost T and X. All right, so space and time, Newton. Gravity is an attractive force between massive bodies. 1687. Works really well. We sent New Horizons to Pluto. It sent us back pictures. We know what Pluto looks like. We sent some of the remains of Clyde Tombaugh, who discovered Pluto, out to Pluto. He's now gone back past it. His remains have gone farther from Earth than any other human beings. So they work really well. But space-time of Einstein, that's also real. And he said mass tells space how to curve, and space tells mass how to move. And mass tells time how to flow. Gravity slows time. All of you who come to the Adirondacks, you know, once you get here, the time goes faster. Yeah, there's a physical reason for this. And the GPS system has to account for this. They're up higher. They're in a lower gravitational field. Their clocks run faster than the clocks here on the surface. It's amazing. It's everywhere. If you use what are those things called? The Garmin, I'm spacing on the name. If you use one of these GPS devices, you're having to use general relativity to be that accurate. So, oh yeah, that warp. Yeah, it shouldn't be a 2D warp. It should be 3D. But I can't draw that. So we have to deal with that. Okay, the other thing well, mass tells space how to bend, and then space tells light how to bend. So in Newton's universe, you have the sun there and the earth. The starlight comes straight past the sun and the earth doesn't notice it's been by. In Einstein's universe, the gravitational pull of the sun bends that light. And so remember, we are utterly convinced that light goes straight. And so when we look back along that ray of light, we say, oh, look, the star is in a different position. That's what Einstein predicted, it was observed by Arthur Eddington in 1919, a century ago. And there's his image from the eclipse where he, those are the stars, he measured their positions and they were deflected from their known positions by exactly the amount that Einstein had predicted. So the Einstein, oh, I misspelled his name, didn't I? I apologize. I was typing quickly. So space, we call it a fabric, but in 3D, it's really a fluid. So the person who asked, what should a 10-year-old take away from this? That space is a fluid. It's like air. Air is a fluid. When I teach global climate and I'm teaching meteorology, I'm always telling my students, we walk around on the bottom of an ocean of air, and there are currents up and down and side to side, and that's what creates weather and storms and all of that. Space is a fluid too. It's something, it's not nothing. And gravitational disturbances will propagate, just like, you know, you have an explosion, you get, in the air, you get the shock wave. You have a bolt of lightning, you get the sound. Gravitational disturbances disturb space-time, and they're going to propagate as gravitational waves, moving at the speed of light, 186,000 miles per second. This is the fabric of space, or the fluid of space expanding and contracting, and nothing reflects, refracts, or absorbs them. You can't draw a shade to keep out the gravity waves. So, and the other thing is they're shaped by the physics that creates them, like air waves. Sonic waves is how we detect air waves. So space-time ripples. Can we detect these ripples, and what can they teach us? So here's what we've known. This is astronomy before 2015. We have information about the universe that is material. We've got the Earth, we've got moon rocks, we've got meteorites. All right, and there's a variety of those things. But everything else other than the Earth, moon rocks, and meteorites, all the other information we have about the universe, the stars, the galaxies, the black holes, all of that has come to us with electromagnetic radiation. Visible radiation, radio, infrared, ultraviolet, X-rays, gamma rays. I'm a radio astronomer. I look at the universe in radio waves. And here is a nice image. The visible, you kind of recognize as the grays. Radio is the purple. The blue is X-ray emission, and the red is infrared emission. So the universe looks very different when you look at these different wave bands. So what can the ripples teach us? Well, let's look. So what creates gravitational waves? You have to thump the fluid like a lightning bolt. Dramatic changes of large masses. Supernovae, where gigantic stars explode and they convert a lot of mass to energy. It's like a tsunami. Massive bodies falling into black holes. Neutron stars fall into black holes. Massive collisions between neutron stars or mergers of black holes. And we've seen both of these now in gravitational waves. What does it look like when gravitational waves pass through the Earth? Because they're passing through the Earth all the time from every direction. This is greatly exaggerated. So this is from the observatory that detects gravitational waves, LIGO. So it's a contraction and expansion of space itself. Every meter stick becomes, you know, a longer meter stick and a shorter meter stick. That's the gravitational wave. So people thought, oh, well, we should be able to detect these, all right? They were predicted by Einstein in 1916. Let's get with the program here. And so in the 60s, this guy, Weber, he made these cylinders of aluminum, and he thought they'd be deformed by the gravitational waves. So he had careful measurements of the size. He thought he made a couple of detections in 69 and 70, but no, he didn't detect them. So we needed a more sensitive instrument. So we're going to use light as our measuring instrument by using a thing called interference. All interference is a fancy word for addition. Here's a wave, crest and trough. It's added to a wave where the crests line up and the troughs line up. You get double the wave. If you add it up with the crests lined up with the troughs, they flatline. That's destructive interference. When they add together, it's constructive interference. You see this in water waves all the time. Throw two rocks into a pond. And here, some places, both crests add, you get a taller wave. Some places, the crest adds to the trough, so you don't have a wave there. And this is how we do it with light, is a double slit. Here it is in water. You've all seen this. This isn't news. So we can build these things. And so we send light to, this is a half silvered mirror or a beam splitter. And so part of the beam goes through, part of the beam gets reflected, then they reflect off other mirrors, come back together, add together, and hit the detector. So if they come back together, they start out aligned crest to crest and trough to trough. If they come back together and they're still crest to crest and trough to trough, then you'll see light. When they come back together and they're crest to trough and trough to crest, you'll see dark. And we see this. We do this in the physics lab. You can come over to Bucas anytime we're back in school. We'll show you this. And we have little machines a lot like this. And so you send a laser beam through here and it bounces around. And I guess it's coming in here. It bounces off these mirrors and comes back together. This is what you see, these rings of where they've interfered constructively, so you have light, where they've destroyed each other, so you have dark. Let's do this on a larger scale. Oh yeah, the fringes. So we have two interferometers in the United States at Hannaford and Livingston. They're not aligned, and both of these detectors have to detect the same signal within 10 milliseconds. So here they are. They have different orientations, so that it's not going to just be an earthquake, you know. This ripple has to come from different directions. It has to hit them both, and it doesn't matter which way they're facing. They're going to expand and contract according to the wave because it's a three-dimensional thing. And then there are mirrors. Here's a mirror, here's a mirror. I know they call them test masses, but they're physicists. What do you expect? And the beams actually reflect between these mirrors 280 times. So the light actually travels 1,100 kilometers. So what does this do? Let's watch another little animation here. And so you're going to see light comes out of that, and then it splits, and it comes back together at the detector here. So now let's watch the waves. So the wave splits. They're actually not different colors. They're the same color, but for illustrative purposes. And so when they come back together, now these are going to meet crest to trough. So there's no detection. There's no light at the detector. It's dark. But now let's stop it and jiggle the mirror. Now you can see they align and they disalign. When they align, you get light. When they disalign, you don't get light. And it's this flashing, this brightening and darkening. This is what LIGO detects, this brightening and darkening of this signal. Very complicated machine to see flashing. So they send these light beams down vacuum tubes that are 4 kilometers long. Earth curves a meter in 4 kilometers. And so they had to get them perfectly straight using GPS. And they're 1.2 meters in diameter, So here's a guy next to it, so it's a little more than 3 feet, and it's a continuous spiral weld that you can see on this thing. So they don't want the tube to disturb the light beams. They're also vacuum tubes. They're at 1/1,000,000th of atmospheric pressure, so they don't get any air vibrations. They don't have any mirages. And it takes them 40 days to pump them down to that low of pressure, that incredibly strong a vacuum. And they have 3 millimeters thick walls that are reinforced, and they have to withstand stresses for 20 years, which every time I give this lecture seems like a shorter time. So the mirrors are these very special mirrors. You can see how reflective it is. And here's just the glass, and then they coat it with probably aluminum or something. And here it is installed, and there's all this stuff on top of it. And the mirror, by the way, is smoothed to surface variations less than a nanometer. So, you know, the hills and valleys on the surface are less than a nanometer in height difference. And so they have all this complicated stuff. So they can measure changes in the path difference across that 1,100 kilometers, mind you. They can measure changes in that path down to 10 to the 19th meters. 10 to the minus 19th. That's 1/10,000th of the diameter of a proton. Imagine that. We can actually measure changes in distance down to 1/10,000th of the diameter of a proton. How do we do this? There's lots of normal vibrations. How come we're not detecting those? There's earthquakes, there's trucks on the roads, there's jogging staff members. Well, in one way, we do it like your noise canceling headphones. We do active damping. And so what your headphones do is they detect incoming sound, and they create exactly the opposite wave so that they match peak to trough and trough to peak. And so we do some of that, but then there's also passive damping. All this stuff that's hanging there, that is all to just damp out the vibrations. We know, you know, Earth has given frequencies of waves. We know what those are. We can damp those out. And these are 40 kilogram masses, so they're heavy. They're glass fibers holding them up so they don't respond to temperature changes or humidity. And the test mass is just the mirror. Here's the detection. This was life-changing for astronomers. And so at 5:51 a.m. on September 14th, 2015, Livingston, it detected this signal, and then 7 milliseconds later, Hannaford got the same signal. They're the same shape. Yeah, there's noise, but there's always noise. The exact shape was predicted by theory. And the calculations of what created this shape shows that it was the merger of 2 black holes in the southern hemisphere's sky. And so the difference in timing was 7 milliseconds. If it had gone straight along the line between the two, the difference in detection would have been 10 milliseconds, so it had to come at it at an angle. And so we could draw this torus of the possible places in the sky this could have come from, because we can't tell anything about the direction perpendicular to this. So this is what they came up with. So they're 10% confident it came from in here, 90% confident it came from in here or up here. And there is some Sirius, the Orion Nebula, some of you have seen that, the southern celestial pole. Now our resolution is improving because more countries are building interferometers. And so in particular, the second detection was aided in its position by the fact that it was also observed by the Italians, because they do have a gravity interferometer. So the event, it was the merger of 2 black holes, 29 and 36 times more massive than the sun, 3 solar masses. M sub, the circle with the dot in the middle is the symbol for the sun. So that's 3 masses of the sun, were converted completely into energy. That's the energy that went into the gravitational waves. That energy doesn't dissipate. And so by E equals mc squared, that's 3 times the mass of the sun times the speed of light squared. Here are the numbers. That's 1.5 times 10 to the 41 kilowatt hours. That's a lot of kilowatt hours, and I pay 6.5 cents for every kilowatt hour I use. So if you translate that into what NIMO or what National Grid would make off me buying that, it'd be 9.75 times 10 to the $39. Yeah, that'd pay for Corona. All right. So we're going to look at a simulation of what this collision would have looked like, and they represent black holes. Why this is a black hole? Why do we represent these this way? And it's because light bends around black holes. And so here's, this is my fellow astronomer, Jeff Miller. That's not me. Looking at the image of this star over here because it bent all the way around the black hole. So this is, so here are these 2 black holes, one slightly bigger than the other. So as they orbit around each other, they're going to go faster and faster, and they are slowly coming together. You can see how the images of everything, a lot of this stuff is behind us as we're looking at these black holes. And so they'll get closer and closer, and then it all settles down quite happily. It was an event. It sent this one ripple. You know, you throw a rock into a pond, you get a series of ripples, and then that's it. That happened 1.3 billion years ago. Life on Earth in that 1.3 billion years has evolved from pond scum into plants, fish, reptiles, and mammals that became humans. Humans have discovered gravity waves, and we built LIGO just in time to detect that jiggle. Cowabunga, this is such exciting stuff. I don't see why anybody would not be a physicist. This is just so cool. All right, eclipses. These are important. We had one in 2017. I went off to Kansas, by gum, and got clouded out. So in 2024, we have another chance, and there's a place here in Missouri that has been in totality of both. And so let's look at, here is the path. There's Canton, right in the path of totality. Whoa! Yes, there's the information. And so now I can read it. 3 minutes and 10.7 seconds of totality. We had 2 minutes in Kansas. Wow! At, well, between 3:24 and 3:27 p.m. On, April 8th. St. Lawrence in April. But it will get dark. No matter what, it got dark in Kansas. I'd really like to be able to see it. So, well, let's hope. Okay, any of you burn incense, you know, do dances, you know, pray. All right, we need your help to see that eclipse in April. All right, September would be so much better. All right, so multi-messenger astronomy. So I told you what we had seen before. We have stuff and electromagnetic waves. Well, the gravitational waves, we detected the first one it arrived in 2015. Then we discovered one, so this is gravitational wave 170817. All right, so August 17, 2017. at 8:41 a.m. Eastern Daylight Time. So the gravitational wave, LIGO detected it at Hannaford and Livingston. 1.74 seconds later, the Fermi Gamma Ray Observatory, this guy, observed a gamma ray burst. It was kind of faint, but they saw it. And it was the merger of two neutron stars. How did we figure that out? Because it was seen in gravitational waves, which told us the masses, in gamma rays, X-rays, ultraviolet, visible, infrared, and radio. We saw it in every band of the spectrum. And it solved the puzzle we had, because gold is very hard stuff to make. And what the sun is doing right now is it's fusing hydrogen into helium. That's not too hard. All the stars do it. We did it in the hydrogen bomb. It's not recommended on the surface of the Earth. But at a nuclear plant conveniently located 93 million miles away, it's perfectly fine. Except don't stay out in the sun too long. It'll burn you. And and then larger stars take the helium and they make it into carbon, oxygen, all of this stuff. When you breathe in, that oxygen was actually released into the universe by the explosion of a giant star that lived and died before the sun. More than 5 billion years ago, this star exploded. And you breathe it. It's amazing. But we can get up to iron, but then it's really hard to make the elements heavier than iron. Gold is a really heavy element. Turns out that gold, how many of you are wearing gold? You got a ring? All right, you know, do you have an earring? You know where that stuff came from? From the merger of two neutron stars more than 5 billion years ago. It's amazing stuff. Just amazing. And this merger of these two neutron stars, it produced an Earth mass of gold. Awesome stuff. And so we wouldn't have known, we would have seen the flash, but we haven't known what gamma ray bursts are. And so observations by more than 70 telescopes followed from these detections, and including neutrinos. And it's a new era in astronomy. I don't have time to explain neutrinos. It's a totally new era. So so this image in the background, this is a Hubble, this is a visible image. So this is the event, this is all that we saw, it's a cloud of expanding stuff. And here, the Chandra is the X-ray observatory. And so it started seeing, this is where it was looking on 8/19, and the jet was initially invisible to Chandra because it was very narrow. It could faintly see some X-ray stuff, but not very bright. Here's Chandra. It's orbiting Earth. It's not out here by this galaxy. And so then a few days later, the jet widened it, ran into some cosmic stuff, gas and dust surrounding this star, stuff in the galaxy, and it ran into it and spread out, just like hose against the wall. And then when it was wider, it moved into Chandra's field of view. Awesome. So the PI, or the Chandra site, says this: this is the first time astronomers have all of the necessary pieces of information of neutron stars merging from the production of gravitational waves, followed by signals in gamma rays, X-rays, optical, and infrared light that all agree with predictions for a short gamma ray burst viewed off axis. We've been really puzzled by these gamma ray bursts. And the gravitational waves gave us this important piece, the masses of the bodies involved in this. And remember, to be science, you got to make predictions. And then take your predictions out in the universe and whack it. Try and break your prediction against the universe. Try and observe something that can confirm or deny your prediction. And this confirmed what we had theoretically said about the mergers of black holes, where the gold comes from. Daryl Haggard at McGill, an assistant professor at McGill, very early in her career, she said, PI is primary investigator. She said, this is a big deal because it's an entirely new level of knowledge. This discovery allows us to link this gravitational wave source up to all the rest of astrophysics. Stars, galaxies, explosions, growing massive black holes, and of course, neutron star mergers, which is what her team detected. Space-time is, in truth, a fluid. It ripples. What other amazing stuff can we learn from these ripples, plus all the telescopes we already have? Thanks. The adventure of being an astronomer continues. All right, let me escape out here and stop sharing so we can see each other again.
Awesome, Eileen. Thank you so much. I just want to pose it to any questions out there. Feel free to pop on and ask your question of Eileen. Okay, I can see Heidi, so how about you go ahead?
Hey, I wrote a question to Victoria. Are there ways to prevent the effects of an EMP, an electromagnetic pulse, used as a weapon, from impacting us here in the US?
No. I mean, you can do it locally by creating a Faraday cage. All right, so what that means is you live in a metal box. If you notice back in the olden days when we had, stereos and you had the, you'd buy this metal box and they had all the electronic components in it. That metal box prevents stray electromagnetic waves from getting into the components. So you can live in a metal box, but we can't cover everything with a metal box. So no, we're vulnerable to that.
Thank you.
And if there's a nearby supernova, we'll find out what the effects are. But fortunately, the big stars that are going to do that are very far away. We're safe. So, and I did have some questions. I'm trying to find the list. Let's see, a few questions. All right, so I had, I talked about what does a 10-year-old need to know. That space-time is a fluid. What's the next question or challenge in the universe that you would like to see answered or conquered beyond this pandemic? Well, since I study galaxies, I'd really like to learn about galaxies. I'd really like to know what dark matter is. That's my big thing. What is dark matter? Dark matter, we see it. The dark matter, we claim it's there because galaxies rotate. The stars, like the sun, is going around the center of the galaxy so fast that if we know, okay, a star of this mass gives us this much light. So we can add up all the light in the galaxy and we can say how much mass that is corresponds to, and so we can say how much mass there is in the galaxy. It's not enough to hold the sun. It's like Earth goes around the sun. The sun has enough mass to hold the Earth to it. But the galaxy doesn't have enough mass to hold the sun to let the sun go as fast as it's going. There's got to be more mass than the stuff we see. And the same is true about galaxy clusters. And so where the galaxies are moving too fast, they should fly apart. And so we've said there's got to be some matter we can't see, dark matter. And I'd really like to know what it is. That's probably, you know, one of my first questions. If I get to meet God, what's dark matter? So that's my question. Other questions?
Yeah, it's been a long time since I took physics with Mr. Bieber in 1968.
Yeah.
So you're my first physics lecturer since then.
Oh, well, you're welcome to come to class anytime, Tom.
So
I can send you my
There you go.
screencasts.
this search you have for dark matter, it's certainly a question anybody, if they thought about it, they'd like to know the answer to. Does that have anything to do with black holes? Is it the stuff inside of a black hole? I mean, how does you theorize? Do they have anything to do with each other?
Well, the black hole matter is very concentrated.
Yes.
And there are black holes in galaxies, but the dark matter is so much more massive. I mean,
Okay.
the dark matter that we need in the Milky Way is 9 times the mass of the stuff that glows. You're not going to make that out of black holes.
I see. The black hole is minor compared to dark matter.
Yeah, they're tiny.
In the black hole, you've got the molecular structures all collapsed down to the basic.
Right. You have
All
space
the
and
space
time
is
and
gone.
matter and energy collapsed into
All the space
stuff
is gone, right? It's one lump.
Yeah. Yeah, because basically.
Okay, so dark matter is even way beyond a black hole's sort of physical
Yeah,
structure.
but
Wow.
it seems it's distributed throughout the universe. So.
And you can
And-
because of the behavior of universes and galaxies and things like that, you have to have the size of dark matter to explain it.
The mass of dark matter. The only
Yes.
way it seems to interact with anything is through its gravity. And the research group I'm with, we're trying to measure, there's this supercluster of galaxies, a long string of galaxies in the fall sky in Pisces and Perseus. And we're observing all those galaxies and trying to measure their actual distances and then the speeds at which they're moving relative to us to determine how fast are they falling into, we think it's a filament of dark matter. How fast are they all falling into the dark matter so that we can measure the mass distribution of this filament of dark matter? We still won't know what it is, but we'll know how much mass it has, which is a very weird thing. So.
Is there any chance that's solved in our lifetime?
I don't know. We've got a lot of people working on it, but yeah, I don't know. But I hope, you know.
Yeah, yeah.
And who knows? Maybe we'll, you know, discover yet another way to measure the universe. So. Wow, there's a whole bunch of people here, so thank you all for coming in. And yeah, the COVID adventure continues. I have to say, I think all of us, to a person, I don't like teaching online. I need the interactions with the students. And it was all of my students, if you were on Jeff's webinar this earlier, he was saying how it's, you know, there were all these people saying that, well, now that you have the internet, universities are obsolete. But no, we're not. It's the interaction is so important. And the students had all the work of college without any of the fun or the personal growth or the, you know, the athletics, all of that. They're living with mom and dad, mowing the lawn, cleaning, doing the dishes, going to college. We all lost a lot not being together. And yeah, Zoom just doesn't it doesn't replace face-to-face. It really doesn't. So, Doing
Well-
research in my house is fine.
Hold on that the conviction and help the community figure out how to communicate that. I believe it. And it was nice to hear Jeff, I caught Jeff's talk, most of it, that the seniors are a good cohort to reference in terms of how they feel about it right now.
Oh, yeah.
And wish they'd made even better use out of what they had. And so that differentiation is really helpful to understand as we go forward and be able to communicate the value of what we're doing.
Yeah, and, you know, before we had to go home, you know, I would give my class a break because it's a 2-hour class, and they would all instantly pull out their phones. They wouldn't talk to each other. My wager is that when we come back, they won't pull out their phones. They'll talk to each other. Some of them still will for some things, but that they're going to value being with other students more than they did.
Yep, well, that's a really essential learning. I started to take notes through your talk, and then I decided I was ruining the value of it, so I just let it go.
Well, you know, I mean, I'm happy to, you know, put the PowerPoint somewhere so it can be accessed.
I
And you
mean,
can grab that.
I think that's helpful if Victoria can make that available.
Yeah, she can facilitate that. Yeah, that's easy.
Because having heard it now, we can reference it, and at least it'll make some sense.
And I embed the internet links in there. Some of the images, if you just click on them, that you can get to the website where that's explained, like the LIGO website and stuff. LIGO has amazing videos to watch, so.
Yeah,
Nice.
I know I can definitely provide that information to everybody here that attended today, certainly, because yeah, it was quite fascinating. And unless there are any other questions out there, I know Eileen, I just had one in terms of maybe as you're looking in reflection of this year or looking towards the fall, maybe what's a course that you're looking forward to teaching?
Oh, the astronomy, actually, the astronomy class it's just a gas. It's a lot of fun to teach. Although it's a lot of hard work, and Jeff was talking about resilience in the students, right? And doing things that they don't expect to do. And students come to astronomy class and they think, oh, we're going to go look at the sky. And then I give them calculators and say, no, we're going to calculate the luminosity of Betelgeuse from the data in the book. And they're like, math? I don't like math. And I spend the whole semester cheerleading about math. And that, you know, look, if you let math intimidate you, you necessarily let people who use math intimidate you, and that's not the kind of power you can give away. And yeah, they have to deal with Excel and stuff, but it's a lot of fun watching them overcome their phobia and also to engage with how big the universe is. So many people seem to kind of live in a shopping mall, you know, and somebody in the government determines what color the sky is today. And to get them to realize that they're on a dust ball spinning, sitting in the lab, they're moving at 742 miles an hour to the east, and the planet is moving at 66,000 miles an hour to go around the sun, and the sun is moving at a ridiculous velocity in the galaxy. All of a sudden, it's like they get out of their little tiny shell, and that's a lot of fun. But then classical mechanics, it's a junior level physics class. It's Newtonian mechanics. It's blocks sliding down planes and stuff. It's a lot of fun to teach because actually, some of us are old enough to remember the song that was a hit in the 60s, Dominique. Dominica, Nika, Nika, study. Yeah. Well, I make it up for mechanics. And it's Mechanica, Nika, Nika, study of all of the stuff you thought you understood. But with pendulums and springs and other oscillating things, it makes your head feel made of wood. And it's fun to watch my students grapple with, geez, I thought I understood this. And yeah, so I love teaching. I mean, you know, and I'm always telling my students, I teach for free. They got to pay me to grade. So,
Awesome.
and that's the utter truth.
Well, that's great. And thank you again, everybody, for tuning in, not only to today's, but I know many were participating yesterday. We were really happy to be able to offer these opportunities, and know from us that they're likely not the only opportunities that we'll you know, be offering over the coming weeks and months. So definitely stay tuned. I know we have some new platforms. Laurentian Connection is really great to connect with, you know, the current students as well as the most recent graduating seniors. And then we also have our Alumni Association Facebook page. So we'll have pictures and updates, and certainly just stay tuned for more news about different events and opportunities that we'll be offering over the summer. And certainly, one more thing before we go, the Brewer Bookstore is offering that 20% off coupon. So don't forget to use your code sometime before Monday at midnight. So thank you everyone for tuning in, and I hope everyone has a great weekend.
Thanks, everyone. It's been fun.
Thank you, Eileen.
It's great fun, Eileen. Thank you.
See ya.
Thank you, Victoria.